Peering deep into the universe, astronomers probe the clash of cosmic forces. The obliteration of matter and energy. We glimpse the limits of time and space in the strange death of a star. There is no vision more reassuring. The endless cycles of the sun and the moon. The heavens ceaselessly turning. The night sky appears eternal and unchanging. Modern astronomy has given us a much different vision of a universe that roils and vents its rage. That vision comes together in the death throes of a giant star. Its surface is a stormy sea of fire. As superheated gas rises and sinks. Giant waves form. Solar tsunamis 1,000 kilometers high. Immense loops of hot, electrified gas, larger than the Earth, blast into its atmosphere. Deep within its core, the star has begun to collapse in on itself. That causes the star to erupt in a violent supernova. In its wake, the explosion leaves a trail of colorful filaments and luminous, billowing clouds. Remarkably, the death of one star gives rise to a whole new generation of others. This cycle of death and birth has defined the history of our Milky Way galaxy and that of billions of other galaxies in the universe beyond. Our own vision of space has been shaped by a handful of rare exploding stars bright enough to be seen by the naked eye. In the year 1054, stargazers in North America spotted a supernova near a crescent moon. The same event was recorded in China, Korea, and the Middle East. The astronomer Tycho Brahe saw one in 1572. He wrote, "I was led into such perplexity by the unbelievability of the thing that I began to doubt the faith of my own eyes." Johannes Kepler recorded the next one in 1604. Galileo used it to make his case for a whole new approach to astronomy, based on the idea that change is a fundamental part of the cosmos. To find out how stars shape our universe, astronomers are employing an arsenal of new technology. From giant telescopes perched on high mountains to a fleet of instruments in space. When we look through a telescope at the stars, we are seeing the visible light they emit. But this is just a small part of what is known as the electromagnetic spectrum. At one end of this spectrum are short, high-energy X-rays and gamma rays. At the other end, long, low-energy radio waves. Huge arrays of radio telescopes are now being used to collect low-energy radio signals emitted by stars far off in the universe. Scientists use them to look through nebulas and gas clouds, to see the objects inside. At the other end of the spectrum are ultraviolet, X-rays, and gamma rays. The short wavelength of X-rays allow doctors to send them through our bodies to look for bone fractures. Astronomers look for them in space as evidence of the most violent processes in our universe. What shapes the cosmos at large is visible close to home. Our Sun is a medium-sized star with a surface temperature of nearly 6,000 degrees Celsius. Deep within its core, the temperature rises to 15 million degrees Celsius. High heat and pressure initiate nuclear fusion reactions that convert hydrogen to helium, releasing energy. The Sun, like all other stars, spends its life fighting gravity. Energy pushing out from its core keeps its outer layers from collapsing in. The Sun produces enough energy to hold gravity in check for billions of years. Not so for a large star. It burns hot and fast, steadily packing its core with heavier and heavier elements. When its core reaches a critical threshold, it no longer produces enough energy to counter gravity. It collapses, then explodes. Destruction is by no means a supernova's only legacy. The explosion seeds its environment with carbon, oxygen, iron, and other elements necessary for life as we know it. Shock waves from the blast can trigger the birth of new stars. In fact, star hatcheries set in motion by supernovae percolate all around our galaxy. Among them is a great luminous cloud of gas and dust known as the Orion Nebula. Here, astronomers have pinpointed solar systems in the making. When clouds like these become dense enough, nuclear fusion begins. Stars and solar systems are born. Another fate altogether awaits the exploding star at the center of this cosmic drama. In the wake of the blast, its highly compressed core remains intact. Imagine planet Earth compressed down to a tennis ball. That's a neutron star. Some can spin at incredible speeds, hundreds of times per second. When a so-called pulsar was first detected by radio telescopes, its signal was thought to have come from a faraway alien civilization. The Crab Nebula is the shell of the same supernova that caught the attention of so many cultures in the year 1054. Scientists have zeroed in on a pulsar deep within. They documented waves of radiation that have etched circular patterns in the surrounding gas. Some dying stars meet a fate that is stranger still. Nature, it seems, has contrived a monster. The scientist Albert Einstein once speculated about a star with such intense gravity that nothing, not even light, could escape its grasp. He dismissed this prospect as impossible. What once seemed beyond reason now defines the frontiers of science. Astronomers believe that when a star explodes, enough matter can collapse into its core that it literally exits the known universe. Gravity wins the final battle. From our vantage on Earth, we define our universe by familiar criteria, including the forms of light we find along the electromagnetic spectrum. But black holes defy discovery. How can we detect an object that emits no light? Astronomers spotted the answer in a flash of gamma radiation in the direction of the center of our galaxy. Radio telescopes zeroed in on the source and found jets of matter racing out in two directions. This is what they saw. A black hole that is drawing a stream of gas from a star's outer layers. As it flows in, it forms a spinning disk. The disk generates magnetic fields that twist around and channel some of the inflowing matter out into a pair of high-energy beams, or jets. Astronomers now know that black holes can pack so much energy into these jets that they accelerate to within a tiny fraction of the speed of light. It turns out that this black hole, known to us as GRO J1655-40, is streaking across space at a speed of 400,000 kilometers per hour, 4 times faster than other stars around it. Most likely, it was blasted like a cannon by the supernova that produced it. Black holes, with their ability to marshal extreme energies, are more than just curiosities in our universe. There is a breed of large black holes that dates back to the earliest times, when the first generation of stars were being born at a rapid pace. When these primordial giants died, some gave birth to black holes. Gravity force-fed these black holes a diet of stars and gas as matter collapsed into the first galaxies, and as small galaxies merged into larger ones. A few of these primordial monsters grew to billions of times the mass of our Sun. By launching powerful jets, they heated up the regions surrounding their host galaxies. That put a stop to the flow of gas into the central galaxy, stunting its growth and allowing smaller galaxies on the periphery to form and grow. But the impact of these black holes did not stop there. This image from the Chandra X-ray Observatory shows a cluster of galaxies called Hydra A. It's enveloped in immense hot cavities glowing in X-ray light. There is a jet visible in radio waves blasting out of its central galaxy. Gas along the edge of the jet was found to contain high levels of iron and other metals, probably generated by supernova explosions. By pushing these metals into regions beyond, the black hole seeded more distant galaxies with the elements needed to form stars and solar systems like ours. Supermassive black holes can be seen in nearly every large galaxy in our universe. We've caught a growing number in the act of powering massive jets. We are beneficiaries of the violent life cycles of stars. And yet, we are separated from them by scales of distance and time beyond anything we experience on Earth. That separation is thrown into sharp relief by the flight of the twin Voyager spacecraft launched in 1977. After exploring the outer planets and their moons, these crafts are now plying the outer limits of the solar system. Tens of billions of miles from Earth. Traveling at 16 kilometers per second, Voyager 2 will pass within 4 light-years of the nearby star Sirius. 290,000 years from now. From our tiny corner of the galaxy, we've discovered that stars not only light up the universe, they also seed it with the stuff of life. By witnessing the explosive end of a star, we gain fleeting glimpses into the power that shapes the universe and transforms worlds like our own.